I will speak about stochastic Cahn-Hilliard equation. It was a joint work with Arnaud Debuche during my PhD. I will talk a few minutes about physics, just for the context. So the Cahn-Hilliard equation is an equation to describe some physics phenomenon, like fast separation in a binary alloy. So you consider two species, you mix it, and you have this binary alloy, and you try to understand how this binary alloy can have a separation of the two phases. So there are some physics words like the spinodal decomposition. So it is this decomposition in two new phases of the binary alloy. There are some property like mass conservation. It is a very important property, and it is a problem in the theory because we have to treat with this mass conservation. And there are interface minimization. So this is the equation. So you have an evolution in time, and you have the Laplace operator. So it is a fourth order equation, so there are no maximal principles. You have a nonlinear function. This is the function f. This function has a double logarithmic form, so you have singularity in 1 and -1. So you have to understand that u is the ratio between the two species. So you have the two species in a box. When u is 1, this is the species A, and when u is -1, this is the species B. So you have this ratio on the box described by this function u. So this is the deterministic equation on a domain omega.
What does lambda represent?
Lambda is just a parameter. I will explain in the next. Yes. Okay. In this slide. For Cahn and Hilliard, they have tried to understand what is the function f. So they have find that the function should be the derivative of a potential. So this is the potential which describes a regular and uniform binary alloy. So you have two parameters. This is the temperature of the binary alloy and the critical temperature, where the binary alloy is completely homogeneous. So we are mathematicians, so we don't have the constant, so we mix it, and we just have this parameter lambda, which is like a ratio between the temperature and the critical temperature. But it's not very important. Maybe after. So to describe this equation, we have an energy. So this energy is described by two terms. This is the nonlinear terms, which is the potential of the equation. This is the capital F. And you have another term described by a gradient, and it is the term of the energy of the interface. So when you have the two alloy, the two phase in the interface, you have the energy because of the gradient of the solution. So this energy can explain all the dynamics of the solution, because the Cahn-Hilliard equation is just a gradient flow in h-1, so it is the classical Hilbert space. And you have this equation described by the gradient flow. And of course you have some Lyapunov function and compact attractor. So if we draw the energy, we have this picture. So the dash line is when you are near the critical temperature, so you have only one minimum. So the binary alloy is homogeneous, and all the solution is it's the solution is in this minima, so it is an homogeneous solution. The solution u equals 0 is a stationary solution, and you see nothing. But when you are on another temperature, the functional is different, and you have these two wheels in the energy, and the solution will try to reach these two wheels. So you have some phase in this wheel and some other phase in this wheel. Okay. So naturally, the potential is singular in 1 and -1 because the solution cannot have a representation in after 1. Yes, no, it's just a picture to fix the idea, but actually the function, the potential is not singular in 1 and -1 because you have this equation. So the function is not singular because there is a limit, but it is a derivative of this potential which has a singular property. And it is explosion, but not on the picture. So when, since it's difficult to treat all this singularity, the mathematician have tried to understand the Cahn-Hilliard equation with some other function f. So, for example, some polynomial function, and this function should have this property of a double wave potential. So, for the very classical expression. But we have tried to understand the singularity of the Cahn-Hilliard equation. So we have tried some other function with explosion. Here there is two functions which are just singular but just in one point because it's difficult to treat two singularities. So in the first step we have just treated the singularity in one point. So it's in the 0 point. So in the deterministic problem, if we want to treat the singularity, we have to try with some polynomial approximation. So you have the functional which is singular. We have a polynomial approximation of this function, and we try to understand the solution. So we have some a priori estimates. I have just write the equation with the variable w, but it's just for the talk. So you have some a priori estimation on the norm of the solution in H1, the norm of the solution in H minus 1, because you have to remember that it is a gradient flow in H minus 1. You have some estimation about the singular term, and you have estimation about the energy, and all these a priori estimation help us to understand and to construct some solution. Okay, I will show you, for example. So you have in the left you have a box, you have a binary alloy, and you make some simulation. So the two phases separate, and they try to reach each one the double wave. So you have the red part and the blue part. This is the two phases, and they are in each one in each way. So it is in a two-dimensional case, but in the one-dimensional case, it is the same thing. So it is just the beginning of the simulation, but you have the top, it is the blue phase, and the bottom, it is the red phase, if you understand. And you have the two forbidden value, which is -1 and 1. So the solution is in the two wells, so it is near 0.5 and -0.5, and there are some interface between the two phases. So it is classical evolution, but it is very static evolution. So when you are in the stationary state on the left, you are fixed, and anything other appears. So we have, not me, but the physician have had some noise to explain an evolution with microfluctuation, thermal microfluctuation, and they have had a noise. So the noise term will be a Wiener process. So I will create only the one-dimensional case. So you write the equation in this form. So you have the W, which is the Wiener process. And since I am the class B, I will explain with the B class. So, but maybe for everyone it's clear the equivalence. Okay, so let H be an Hilbert space and Q a positive defined symmetric linear operator. We try to construct this object, so you have the eigenvector and the eigenvalue of the operator Q, and you have some beta k, some Brownian motion. In our one-dimensional case, H is just the L2 space on the interval 0, 1, and Q is just a power of the Laplacian, for example, for instance. Given an operator B, so you can think about some derivative operator. This operator can have an effect on the noise term. But if you want that this new object with a derivative operator, if you want it to exist in a new space K, you have some property about the operator B. So he had to have some property about his behavior. Okay, so I will use some notation to rewrite my equation. So maybe you can have in mind just A is the realization of the Laplace operator with Neumann boundary condition. The space W22 is the classical Sobolev space. I have some notation for the inner product in this L2 space and for the average of the solution. You have to remember that the average is very important because the Cahn-Hilliard equation should conserve the average of the solution. So we have to be we have to take care about this average conservation. So we will work on the space L2, but only with the function which have a constant average. So for example, if C is some real, you have L2 C, which is this space. The Q operator in the definition of the Wiener process will be the inverse of the Laplacian. So with this operator, we can define a new space with a new semi-norm and a new inner product. So it will be the space H minus 1, if you have in mind. And we denote this space H as the completion of the L2 space for this new norm, and we have this new inner product. So since the Cahn-Hilliard equation in a gradient flow in H minus 1, we have to work in this space because it is the space of the solution and it is not the L2 space. So we can rewrite the equation in the abstract form. So you have again the nonlinear term f, and you have a process x, and the initial condition is some function in the H space. Okay, just to fix the idea for the linear equation, we can solve this equation. we say that the mild solution is given by the formula, which is just a variation of the constant. So this process is the the solution of the linear problem. And this process, the average of this process is constant, so it is important to have this conservation. Its law is a Gaussian measure. And if you let the time goes to infinity, the law of this process converges to a Gaussian measure. I will denote mu c. It is a Gaussian measure with covariance operator Q, and she is described by, again, this C value. It is just the average of the initial condition X. Okay, so this is the invariant measure of the linear process, and this invariant measure will have a crucial role in the future. So we try to understand with the nonlinear function f this new equation. So we say that for this equation we will try with some polynomial approximation. So I denote fn, the polynomial approximation of f, and we write a mild solution of the equation with the z process, which is the solution of the linear equation, and this term. So we have to show that this solution exists. So it's some classical proof, but we have to show that the solution is in a good space, so it's continuous in time in the H space, and the solution has some LP property. And we can rewrite the equation in this form. So you have the solution xn, and you have the test function h, which are in the domain of the operator a, and you write all the equation in this form. So you see that you have all the derivative can operate on the test function h. So we can write some solution without a lot derivative property. So it's okay, it works, and we have a solution. And the average of this solution is again a constant. So it is just the average of the initial solution. Okay, so we have all these solutions for the approximated equation. We let n goes to infinity, and we want to have a solution, a limit solution for the limit function. Okay, maybe it works, but maybe not. And actually, it doesn't work because there are some problem because of the singularity of the function. So we stopped and we try another idea. So this is the idea of Arnaud Debuche and Lorenzo Zambutti. So they try to understand what is the problem of this singularity. So they have the linear equation, and they add some term. This is the eta term. It is a measure. Why it is a measure? Because you want the solution, you want to avoid that the solution break the forbidden value and explores all the space. So you want to force the solution to stay in an interval, so the interval -1, 1. Okay, it's again too complicated, too difficult, so you only want to force the solution to stay positive. It is the first step. So you have this equation with the solution which is positive. It can describe an evolutionary hard wall. and you try to understand this equation. So you use a penalization method with some, again, approximated equation. So you penalize the negative part of the solution. You let epsilon goes to 0, and you try to understand the limit of this process. Okay. For the linear solution, for the linear problem, you remember we have an invariant measure, which is mu c. And now for this problem, we can write the invariant measure of the equation. So it is some, it is a new measure, mu c, which is described by these weights for the mu c measure, and it is this term is just some function which depends on this term. So you can recognize the primitive of the function. And you have this invariant measure for the problem. Okay, now you have this invariant measure for the problem. You have a stationary solution for the problem. So you try to understand the limit of this invariant measure. So you let epsilon goes to 0 in the invariant measure, and you try to understand the limit. Since we have the negative part of the solution in this term, if the x function has a negative part, this term will be positive, so this term will goes to infinity. So with the minus 1, it will goes to minus infinity, so this is 0 in the limit. So if the solution have a negative part, the limit of the invariant measure is 0. So you can write the mu c measure like this. It is just the mu c measure with some indicatrix function, which is just the indicatrix of the positiveness of the solution. So this measure is now the invariant measure of the top problem in the board. So you have this measure which is only on the space of the function which are positive. So if you have a solution which is distributed in this law, this is a stationary solution of the problem of this problem. So you have succeeded because you have now a solution which is always positive. This is a stationary solution of the problem, and it's okay. You have to understand what is this term. This is a measure, and this is just the limit of this term. So the limit of this term is a measure which it acts only on the point 0. So you can write this condition, u times theta is 0. So when the solution is positive, the measure doesn't act. And when the solution reaches the 0 value, the measure acts and force the solution. Yes?
For the invariant measure means for the t equal to 1.
This invariant measure for?
But the integral from 0 to 1, theta for theta.
Yes, here it is just the space. So we are in.
Oh non, c'est parce que tu as mis R2.
Oh yes. Oh, okay. So, okay. Yeah. This is in the one-dimensional case. Okay. Thank you. Okay. So it is some Lagrange multiplicative. Okay. So now we know how to force a solution to stay positive. So we add the singular term. So with two functions, or for example, a logarithm of the function of the negative power of the solution, and we will try the same thing. if you have in mind the deterministic case, you can write some a priori estimation on this equation, which is again a polynomial approximation of the function, but in the stochastic case. So you have the same terms that in the deterministic case. You have another term due to the Wiener process, and you have some term, which is the difficult part of the equation, because you have to control this term. But it's not a problem if this norm is well defined, because this term is just a constant. So if the B operator is again a good operator, it's not a problem. So we have again a solution. And we will try to understand the invariant measure of this new equation. So we rewrite again the equation in some abstract form, and we have some. We have U. This is a potential which depends on the energy functional F. So this system is now a gradient system, and you can write the invariant measure of this system like before. So you have again a new C measure, which is just it depends on the mu C measure, and you have some extra term, and this term is just a term which depends on the functional of the energy. But this function is not singular, it's just 1 plus u times logarithm 1 plus u. So you have limit in the boundary, so you can treat the problem, you can understand the invariant measure, and you can use all the classical techniques to define some solution of the approximate equation. And again, we have to understand the limit of this invariant measure. So you let n goes to infinity, and again, it is very simple to understand the limit. It is again an indicatrix function of a new space. The space K is the space of the solution which are in -1 and +1. So you have this indicatrix, and you have some extra term, which is just the energy of the limited function f. So you have this new measure, and which is again the invariant measure of our problem. So if you start with an initial data distributed by the law of this measure, you have again a stationary solution, and the solution stay in -1 and +1, and you have again a solution in all time and stationary solution. Okay, I have write this here. So you have a stationary solution for the approximate equation. You let n goes to infinity, so you have a new stationary solution of the singular problem. Moreover, this term, which is the singular term, is well defined, and you can write all the term in the equation without problem. And if we define the difference between the approximate term fn xn and this limited term fx, this is some measure. So it's eta n, and this eta n measure, it is the extra term in the equation. She has a limit, and this limit is some eta function, eta measure. Okay, maybe. Okay. Okay. So you have the equation. This is a singular equation, and you want to simulate this equation. So I draw some pictures about the simulation. So you have the solution on the 0, 1 space. Now it's just for the computation, it's some Dirichlet condition, 0 in 0 and 1. you do the computation, you do the simulation, and you try to understand how to simulate this reflection measure. So we have had a lot of different techniques. I can explain you if you want, but it's not very interesting now. So you have the solution, and the solution, because of the Wiener process, they want to escape of the interval, of the positive interval, and they want to go in the negative part. So you have the measure which act when the solution wants to break the forbidden value, the zero forbidden value. So you can see here in the computation, I have an action of the measure in this point, here is on this point, etc. And which is very interesting because Lorenzo Zambotti show that for such a process, the solution will touch the forbidden value, but only 4 times. So when you do simulation, we have see this solution, and effectively the solution only touch the barrier only 4 times at maximum. So it is a simulation validation of the result of Lorenzo Zambotti. Yes, but in this point it's just a Dirichlet condition, so it doesn't touch the value. Okay, no, it's just for interior of the domain. Yes. Okay. If the function is negative power of the solution, you remember. For this function, we can do the same things, and we have the solution. But if the power of the singular function is greater than 3, the nonlinearity is strong, and if we study the reflection measure for this new function, you can prove that actually this measure is identically null. It shows that if the singularity is not strong enough, we have to add this measure to force the solution to stay positive. For example, in the logarithmic case, we have a measure. For other function we have measure, but for this measure, for example, if the power of the singularity is strong enough, actually there are no measures, so we have a very classical solution of the solution with no measure. Okay. Now with 2 singularity and two measures. So we have again the singular term, which is f, which is this function. So we have singularity in -1 and +1, and you want to add 2 measures. This is a measure which on the 1 point and a measure on the -1 point. So you have two contact conditions which explain this action of the measure. So eta plus only act on the 1 point, and eta minus only act on the -1 point. And again, you can use the same idea to prove we have a solution of this equation. You use some approximated equation. You use some you use the invariant measure. You can write the limit of the invariant measure, so you have a stationary solution. Now you have this stationary solution. You can create a real solution, a strong solution of the process of the equation. And again, it works. But it is more difficult in this problem because you have 2 barriers, so you have to deal with these two conditions. So it's a bit more difficult, but finally it's not a problem. Okay, so now we have 2 limits, 2 barriers. So you have a barrier in -1 and a barrier in +1. you have the singular equation, the singular function, and we want to simulate this solution, so we do the simulation. Okay, the solution again reach some value. It's 0.4 and minus 0.4, and the solution is very close to the deterministic solution, but you have some random forcing, so you have the noise. Yes, I think everyone see the noise on the simulation. And the solution doesn't touch the barrier, so this, again, the simulation shows that the reflection measure maybe we don't have a reflection measure if the singularity are strong enough. Okay. Okay. What about the ergodicity of this invariant measure? So we have this space. I've explained before the space K of the solution which are in the interval -1, 1. We have an initial value in this space and in the H space with this average C. So you have a unique solution and a unique invariant measure, nu C, and this measure is ergodic. Moreover, if C is in the interior of the domain -1, 1, there exists some beta small enough and a constant C such that for all test function, it's some Borel bounded Borelian function. You have this estimation. This is the solution of the problem. So you take this average of the problem. You have the invariant measure. So the solution is close to the invariant measure with some exponential. So the solution is near the invariant measure with exponentially close. Okay, so it's an exponential mixing which explains that actually the solution is always very near of the invariant solution. Okay, thanks for your attention.
Well, in the first case, you had you said that the solution touches the barrier at four positions.
For the first case,
yes,
with just one barrier.
But then but you remember what I'm thinking about. The solution touches the barrier at four times or
yes.
four positions.
Yes.
I understand that the special regularity of the solution is just L2 or something.
Yes.
So can you count the positions?
Okay, I understand. But yes, the solution is more regular than N2. If you have seen this, I don't know if. Yes, you have the approximate solution. They are very regular, so you have some continuity in time, and you can write some regularity of the function, so you have continuity, and you can speak about the points of the function. But for this simulation, okay. We can speak about the points of the solution. It's not just a L2 solution. Okay, there are more regularity of the solution.
It's continuous.
Yes, continuous.
Now, where does this 4 come from? Does it debate if you make the interval longer, will 4 become 5 or something? Is it always 4? Or why 4?
Why 4? It's a good question. It's linked to some you can write the process in another form. It's some three-dimensional Bessel process, bridge process. So all the laws of this process are well known, and since you can represent the solution like this process, you can have the same property of this process than the three-Bessel bridge process. So maybe if you want to know why for, you have to read some books about this process. But
you should ask Robert, because you had mentioned that Robert is a co-author of this work. Am I right?
No, I think you are right, but
Any questions?
when you have Stephen.
Yes.
How difficult is it to extend this to multiple dimensions?
yes, but in higher dimension, it doesn't work because we don't have a good solution just for the linear case. We can't write a good solution. So it's just in the one-dimensional case that we can write a solution and make all these things. It is your question?
Well, there are solutions in multiple dimensions. What is it that is missing?
Actually, it's the control of the isotherm in the a priori, in the estimate. Oh, where is it? Okay. So the problem is this term, because you have to control this norm of this operator and the structure of the equation. For the structure of the equation, we need that this operator B is related to the Laplace operator. So it is a given operator. So you have to control this term. But in the one-dimensional case, it's okay. You can write explicitly what is this term, what is this norm of the operator. But in the two-dimensional case, you can write this term, and it's just infinity. So you have nothing in this estimation. You have just infinity.
Question also. So you add this penalty and proof of work. Do you know anything about the rate?
The rate
Yeah.
of the convergence?
Yeah.
I don't know. No.
I was thinking, if you want to distinguish different penalties, is there a method to look, or could you look? I guess to look on the rate would be one way to
Yes.
say which is.
Maybe we can see some convergence and some rate of convergence, but I think it's very difficult because we can't compare the solution for two different epsilon for the solution. Numerically, it's possible, so maybe we can do some simulation. But again, it's difficult to compare the solution because you have the noise. So I don't know how I can compare the solution. Maybe if I take some average, but if I take average, it's just deterministic solution. So I don't know, but maybe.
Yeah. Let's thank the speaker again.